How coordination functions during running is very complicated. Coordination can be seen as a sphere created from layers or shells with the plan for the intended movement designed at the center. Each shell represents an important aspect of coordination. To learn more about how running functions, one can observe the legs, arms and trunk as they move. The up and downward motion of the legs can be caught on video. Such images will supply information, for example, about angular changes in the ankle, knee and hip joints. This process is found in the outer shell of coordination. It is more difficult to observe how muscles work together in precision to bring about the motion called running. Such collaboration between muscles is called intermuscular coordination, which forms the next inner layer of the coordination sphere. By measuring electrical activity in muscle, scientists are able to chart when certain muscles are active during running. A noteworthy finding is that a large number of muscles are actually active at the beginning of the landing. However, far fewer muscles are at work as the knee is stretched during push-off. It is difficult to ascertain which individual muscle is working during running, even when using advanced scientific methods for research. For example, more is now known about the structure and function of a muscle by studying its tissue under a microscope. A muscle contains one segment that can shorten and one that resembles an elastic band or spring. Later, we will see that this elastic property of muscle plays an important role during running. The action of an individual muscle is called intramuscular coordination and can be found in a separate shell of the coordination sphere. A plan for movement, in this case running, is designed at the center of the sphere. This plan is translated by the brain into signals that are sent down neural pathways to muscles. When analyzing a running technique, one usually will focus on the outermost shell of coordination, thus ignoring whatever is concealed beneath this outer layer. Therefore, valuable information needed to evaluate a running technique sensibly will be lost. Consider the following example. A physicist considers the last part of push-off to be very important because much force can be directed horizontally during thrust. This is correct according to the laws of mechanics. In contrast, however, a biomechanic will immediately note that much less force can be provided because of the position of muscles that stretch the hip at the end of push-off.